I'm here with Steve at the Expo. Steve, you've got an amazing collection of stuff. Tell us a bit about it. I can see right behind us you've got an Osborne in pretty minty condition. How did you come across that?
Yeah, the Osborne one, actually I'm not sure where I got it from, to be honest. It did come originally from what was called Richmond TAFE. Yeah, it had the courses for their open day, and it worked fine, apart from the old reefer capacitor exploding, which people have probably heard of. Yeah. But I didn't know it was the reefer capacitor because the smoke seemed to be coming from the floppy disk drive, which I was very worried about. But after closer examination, it was just the reefer. But there's the disk there from the TAFE. But it didn't have enough information. It didn't have the format utility to make some more disks. So the long drawn-out procedure to download it from the net and image disks. It only has 100K per disk. Mm-hmm. So single-sided, single density.
Yep. This is like really minty as far as Osbornes go. You know, it looks really nice. I'm quite impressed with it.
Yeah, I don't know why it's particularly good condition. I mean, it was kicking around in my garage for a long time. Okay. I don't know. What normally happens is the catches break. The company still exists that makes these catches. You can still buy those catches new.
Yep.
They're just hanging there by almost nothing. They're going to break off any minute.
That's cool. So tell us about, you've got this huge display here, and we'll get to it shortly. Tell us a little bit about some of this stuff. It looks to me there's a lot of late 70s stuff, some kit stuff, some other things. This is the kind of stuff that I do not know about. So I'm completely out of my depth here.
Okay, actually in the late 60s, if you wanted to learn about computers, you'd learn about logic design.
Yep.
So you might find yourself with one of these in a computer lab there with digital. There's a workbook talks about how to design all the circuits simple circuits for computers. Adders, for example, various shift registers and stuff. I've just got wired up as a binary counter there for display. Some of the more advanced projects, you need two of these and you wire them up. You get a big bag of wires to wire up multiple units. A little bit further on, a bit more advanced when microprocessors came about. We've got, for example, this one, the Motorola MEK6800D2. Mm-hmm. This one you can program in hexadecimal. If I plug in an address there, and that's the value at that memory address. This runs at just over 600 kilohertz. Okay. Each of these is got 128 bytes of RAM, or one of them is the ROM. Mm-hmm. So a 6800 processor.
Yep. That's cool.
About the same time, around about 1975, 76, another company made a similar machine. This is also based on a 6800.
Yep.
This one's quite nice. It has the gold-capped memory chips. Yeah. Each one of those is 128 bytes.
Now, this is my hand, and look at how big this thing is.
Yeah, there's a big filter capacitor there. I haven't turned this one on just yet.
Yeah.
Not sure what will happen. It should work. So at the same time, people would recognise the Kim 1. They would know as the Kim 1, which is the beginning of the Commodore computer range of stuff. Synertek systems had the Sim 1, which is Kim 1 compatible.
That's cool.
So a similar machine, you program that in hexadecimal.
50,000 units sold.
Oh, possibly. It's a bit hard to pick how to get this information. This one has a serial interface. You can connect a dumb terminal, or as they intended, a teletype with a paper tape punch, because that's how you would save the programs. Fast forward, that's from 1975. A little bit later on, Texas Instruments brought out this trainer here, which is based on the TMS 9980A processor.
Now this looks like a calculator to the...
because Texas Instruments were making calculators in the day, they would recycle the calculator body, and just there's your keypad and display for programming in hexadecimal again. This is an interesting machine because it's 16-bit, but it only has 1K of RAM still.
Oh, wow. Okay.
All of these machines are 1K or thereabouts, maybe a fraction more.
I like this Tech 1 machine with the LEDs.
The Tech 1 is a kit computer from Talking Electronics in 1983, designed by Ken Stone and John Hardy. So once again, you program it in hexadecimal. I'm just looking, I've run the early monitor on there, so you can just address through or increment through the address space there if you wanted to change the values. I've got a ZIF socket so you can put other bits and pieces. One peripheral that they made, which was quite handy, was a battery backup RAM. Because at the time there was no way to save your programs. You typed them in, you might spend 2 hours typing in. As soon as you turn the power off, it's gone. So Ken designed a battery backup for it, which has been very, very handy. Later on, they made a cassette interface for it. I don't have that on this one. They also made, as you see, the LED display. There was also the LCD interface for it. If I run a program, which I put in there earlier at a location which I forgot the number, 1800, it'll speak.
That's cool. There you go.
So, yep. So I later on put a serial interface onto this one as well, so I can download from the PC. So, many of these were made. There was been a few iterations of these. The Tech 1, this is an original one. Tech 1B. I think they're up to a Tech 1G now, which has just been released. That's designed by Mark there in Sydney. We'll jump over to this one.
Yeah.
So this is the Dream 6800, designed by Mike Bauer. This one, it's a similar machine. It works in hexadecimal and so on. This is the original prototype that Mike gave me.
Wow. That's interesting.
That's what it looks like inside.
Yep.
Except for not for that bit. That's some add-on that somebody put on there.
Okay.
But that's what's inside.
And you've got the documentation.
That's the original article from the magazine from 1979, Electronics Australia.
Wow.
The Dream 6800 was based on the COSMAC VIP from RCA.
That's interesting. I would never have picked RCA doing...
So a fellow by the name of Joseph Weisbecker, I think his name was, he designed a processor at home, the 1802 processor, which is this one, which they've made radiation-hardened versions of it, and they send it up in the Galileo spacecraft.
Oh, wow.
So that processor is still being made, and it's used in a lot of military applications and aeronauticals. So Joseph originally designed this with what's called the Chip 8 interpreter. So that's a simple, predominantly a games-based interpreter. So you program it in 2 bytes of hex for functions. So you didn't program it in assembly, you programmed it in Chip 8. Mike Bauer read about the article in the Byte magazine and designed his own version. It's Chip 8 compatible, but it doesn't use any of Joseph's original information or anything, because Mike had never seen the COSMAC VIP when he designed the Dream 6800.
Okay.
Mike also developed his own assembler so he could write the program for the Dream 6800 as well. So Mike's a very clever fella, and I'm deeply indebted to Mike for giving me his prototype. Moving on, we've got that label's in the wrong spot. That should be there.
That's all right.
That's an Intel trainer there. So that was for the 8085 processor. Once again, program it in hex. And so on. That's the original article for the Tech 1.
Oh, that's cool. This box looks like it's out of some 80s movie where they launched nuclear weapons. Do you know?
This box it looks like I haven't got a lot of information on it. It does work. I have turned it on. It's 8080 based, so fairly early on in terms of processor technology, but the chip dates are around about 1984, so this was still built in around about 1984.
Wow.
The idea being that you could program the processor for control systems. There's a closed loop system, there's a fan with a thermistor.
That's where the explosives go.
Yeah, that's right. And that, the fan runs off the batteries actually. I haven't got the batteries installed. So there's a whole bunch of experiments that you would go through. There's a variable resistor here. A whole bunch of experiments that you would write. There's some code in there. I've got a little bit of information, but I haven't dug into it. But it's fully expanded basically. I don't have information on how this works. There's a serial interface chip there which I'd like to figure out how it's set up.
And this one looks like it's out of Get Smart.
This one is your rocket launcher.
Right.
There's a 400-something page manual on how to use this. This machine's interesting. Whilst you can program it in hexadecimal like all the other ones, fetch address, for example. This machine was just to teach people how to program 8085 assembly, but also for hardware engineers, because there's little jumper settings all around and these switches and so on. You can introduce faults into this. So in a lab setting, maybe the students would go out for a break, the instructor would introduce faults into the board, and when the students come back, they have to figure out how to fix it.
All right.
So there's lots of exercises in the book here, how to use a logic analyzer and signature analyzers in order to fault find and fix it.
Interesting.
Okay, the rocket blast off. So if we just press reset here, and the rocket launch program is at 05F9. So fetch address 05F9, and we run.
That's cool.
All right, there's that one. The other one, there's a stopwatch program. So we run that. I'm not sure how accurate the timing is, but it looks pretty good. 0662. Run. Number 3 starts it. And then 3 stops it. And 0 to reset. So, yeah, you've got a stopwatch there.
That's cool. And when was this made, do you think? What sort of year range?
This one here, well, the book was published in originally 1979.
Right, okay.
So this machine probably is from 1980. It's a little bit later.
Yep.
I'll do one more demo, which is this is rather interesting. I don't understand the name of it exactly. Okay, this is a squirrel feedback shift register display.
Okay. All right, let's see the squirrel, the secret squirrel.
So that one is at 055A and run. Okay.
There you go.
That's a squirrel feedback shift register display. If you watch that long enough, it does actually vary. It changes in shape. And at one point it disappears altogether. You have to read up the theory behind this, because I haven't.
Some trippy computer engineer, I think, did this. There you go.
Yeah, so it does vary. It keeps going. We'll leave it go because it's interesting to look at. Okay, this is a Data General Eclipse C350. It's a 16-bit machine from about 1976.
Yep.
It uses discrete logic CPU boards. All of these boards have got loads of logic on there.
Wow. These are big boards. I mean, look.
An example board is like this.
Oh, there you go. Huge.
This is the controller board for the tape drive.
Yep.
It uses a bit slice processor here. So Data General didn't use commercially available processors. Mm-hmm. They basically created their own processors as needed from bit slice chips that were available at the time.
Really interesting.
So it's a very complicated board. This is fundamentally the complexity on all the other boards. Some are a little simpler.
Yeah.
For example, this board here This is the interface board to the communication chassis, which is down underneath the tape drive. Mm-hmm. So it's a little bit simpler because much of the smarts is on the other board.
I love how you can just pull these boards out.
This is a solid state memory. I have to call it solid state because the earlier ones were based on core memory. This is about 256K of memory.
I'd hate to think how many chips are on there.
It's an interesting episode to service it. You can put multiple boards in the machine and it's all set by these jumpers along here. It's for the address location for each of the boards. The memory was interleaved as well. You could have up to 4-way interleaving in the memory. The fan in the machine here is at the bottom. It uses 3-phase power for the fan to cool the CPU. This is all, behind this is actually fresh air. This is obviously switches to get it going. So the boot sequence to load from tape, for example, you'd be putting in address 1000 and then 2, that's not 2, 1, 2, yeah, 22.
Yeah.
Because these are in octal groups there. And then you press, you press reset to make sure you're in the right spot. And then load program. That would be the theory if it was all plugged in and working. Yeah, 1, that's 1, 2, yeah. Forgot how to count in binary. The 9-track tape drive here. One reel of tape would give you approximately 30 megabytes.
Okay.
It's a vacuum column tape drive to keep the constant tension of tape across the head and the capstan motor here. There's a vacuum columns here. It would suck the tape down here. Okay, obviously not using my finger, but these holes here has got a vacuum pump connected behind there and it would suck that down. There's small holes along the way which would then measure the air pressure difference, so therefore it would know where to position this motor here to get the tape set at a certain height there and the correct tension across the head. There's a high low density. The low density is 800 bits per inch and the high density is 1600 bits per inch. To start the machine, you press power on, you press BOT for beginning of tape.
All right.
So the tape would be loaded in this position here. When you press BOT, the pump would start up and it would suck the tape into the column. Then it would wind the tape forward. I'm not sure exactly how far it is, but there's a bit of like aluminium foil that's stuck on the tape and it would come up and that's a light sensor there shining that way and it would get the reflection of the light there and that would mark the beginning of tape. There's a similar thing at the other end for the end of tape.
Yep.
Then if you want to take your tape off, you press unload. The tapes would wind back to this position, the vacuum would turn off, and it would wind the tape all the way back like this. Somebody's been winding a long way. It would wind it back, there we go. And then it'd be like that. You press the button here to release. There's your tape. This band here is your write protect. So this tape is write protected. If you want to write to it, you take this off. That's your write protect tab, so to speak.
That's very cool. How heavy is that? Could I have picked that up?
Not particularly heavy.
So it's probably about 3 kilos, maybe?
Oh, I don't even think so.
2 kilos?
Yeah, something like, not much.
Yeah.
Yeah, it's 1/2-inch tape. Standard, well, I wouldn't say standard, but your metal oxide sort of material on there. Yeah. Have a look around the back. The comms controller board that we saw before would plug in and come through here. There's a communication chassis there with more boards. Each of these connections here, I think there's 4, a handful of these goes to these connections up above. So you'd have a user piece, a user dumb terminal plugged into each one of these. So with a machine with maybe 4 megabytes of RAM or less, you could have multiple chassis connected up. You could have maybe 60 users connected there. This connector here, that's a Winchester connector which goes off to the disk drive. So that's the interface to the disk drive. This is a disk controller chassis.
So with these dumb terminal connections up here.
Yep.
Is this something the same? When you say dumb terminal, you mean like a VT100?
Exactly
terminal?
like the Data General version of VT100 would be a D200.
Okay. Like I've got a digital VT100, and I remember back in the day using VAXs and things like that.
Yep.
What would be the interface that people would experience when they connected their dumb terminal up?
Similar to what you describe on the VAX systems. These machines would be used, and say an example would be a small library, for example. Anything that's text-based, a database sort of thing. You've got fields like author and this and that. Yeah. Or in a financial setting, stock control, products and descriptions. The fields would be permanently written on the screen, and it would only be the data that would be updated.
Yeah, that's cool.
So this is the back of the CPU cabinet.
Wow.
So the controller cards plug in, and then you plug this interface cable on the back here, which corresponds to the controller card.
Yep.
That goes up to this paddle board up above here. In this case, we've got, we don't have that one. We have this other cable plugged in, which looks like it went off to a printer once upon a time. The next one along is that's the data cable to the tape drive.
That's a chunky ass cable if I've ever seen one.
There's lots of pins involved.
Yeah.
And let's get this off.
My goodness me. That's one of the biggest cables I've ever seen.
Okay.
Wow.
So this machine not only did it require three-phase power for the motor, this power supply is the 5-volt power supply. It's 5 volts at 130 amps. This is a 12-volt power supply at 45 amps.
Yep.
So these were wired on separate phases. And if you had a fully expanded machine, there's obviously a bay for another power supply.
This is huge. Roughly, what do you think it weighs?
I think close to 200 kilos per cabinet.
Oh, as in each one of those?
Something like that.
So that's
because,
at least 400.
I'm not exactly a weightlifter, but I am barely. Well, you try lifting it off the ground just on the corner, and then you'll get an idea how much it weighs.
Okay.
Because you know how much it weighs. You know how much 100 kilos weighs.
Yeah.
And then you can tell me then.
I might do it.
Okay. Let's have a look on
the.
We forgot to have a look at the inside of the tape drive.
Yeah.
So spin around on this side. This is a bit of a sight to behold. The complexity inside here is quite amazing.
Oh, what? How is this a thing?
So all the servo control system for this is all this analog circuitry combined with some digital. There's no microprocessor in here to control the servo system.
Wow.
It can accelerate the tape up to 200 inches per second.
That
you can see the connection to the vacuum pump there.
It's very clean, I want to say, for.
Well, I did dust it out before bringing it to the show. It was filthy everything was black inside I spent a lot of time cleaning it. The whole machine was stored in somebody's shed, and the roof had broken, and birds moved in and nested. It was all covered in bird poo and everything. So I spent a lot of time cleaning it for the show.
Have you thought about what it might take to get up and running again?
Yes, I have.
I know it's a big.
I think it's achievable to make this one work. I have another CPU cabinet with all the boards in it and more memory than what's here. So I've got a lot of spares. That includes power supplies as well. I've got power supplies. I don't have another tape drive like this. I have the older version tape drive. This is a 6026. I've got a 6020 tape drive, which only does 800 BPI. It looks pretty much the same. It's got a perspex here, so you can see everything rather than partially seeing it.
Wow.
But the rubber on the capstan here is decomposed, and that's very critical because the acceleration is so fast on this. If that slips, you get read errors and write errors.
It's a timing thing, yeah.
This has to be clean to a certain level. You can't make it too sticky because then the tape sticks to it, and you can't make it too shiny because then it slips.
So really the only other way of doing it might be to find another one of these.
Another one, yeah. This one is in good condition.
Yep.
I haven't tried it. The cleaning solution of choice is Morning Fresh. So,
fair enough.
So I think there might be a chance to make this work. I think I've got enough boards to make it work, although I'm not sure about the software. I used to service these.
Okay.
I used to have the diagnostic tape, so you could boot the diagnostic operating system from tape.
Wow. What was the operating system that ran on it?
There were two operating systems that the C350 could run, was RDOS or AOS.
Okay.
Okay. AOS was a great multi-user platform. Think of it as like a very primitive Unix type thing.
Yeah.
The application that you would use to create new users was called Predator, profile editor.
Well, that's fantastic.